Hello friends, the topic for today is 8037 instruction set data transfer instructions. The 8087 has 68 instructions. These instructions are divided into 6 groups according to their function: data transfer, arithmetic, comparison, transcendental, constant, and process control. The Intel 387 DX Math coprocessor adds over 70 instructions to the Intel 80386 DX Microprocessor. The instruction set for the 80387 MCP, that is Math coprocessor, is largely the same as that for the 80287 and 8087. In today's video, we will learn the data types supported by 8087, 80387 and data transfer instructions. Let us start. Welcome to our channel Engineering and Technology for You. If you have not subscribed to our channel, kindly subscribe to our channel and press the bell icon. The topic for today is 8037 instruction set. Here we are going to study the instruction set, data transfer instructions and the data formats supported by 8087. Let us start with the introduction, that is register set of 8087 and 387. The 8037 coprocessor has 13 registers. The 8 80-bit floating point data registers, control register, status register, tag register, an instruction pointer and a data pointer. Now figure 1 and 2 shows the register of 8087 and 80387. Let us see the figures. So here you can see, here we have the registers of the CPU, that is 8086, 8088. So all the registers are present here: AX, BX, CX, DX, SI, DI, BP and SP. Then IP and flags are there, and the 4 segment registers are present, and these are the registers of 8087. So these are the data registers R0 to R1 to R8 or R0 to R7, they are designated. Then we have the control register, status register, tag word, instruction pointer and data pointer. Now these registers, data registers, they are having the 3 fields: sign, exponent and significant. We'll see the details when we study the data types. Then similarly 80387, when we study the register set, again we have the same registers R0 to R7, that is the data registers, then control register, status register, tag word, instruction pointer and data pointer, similar to 8087. Only here the registers of Intel 386, they are shown. So that is the extended EAX, EBX, ECX, EDX, ESI, EDI, EBP, ESP. So that is only the difference. And then E flags and EIP. And in the segment registers, we have the 4 segment registers plus the FS and GS, 2 more segment registers which are there in 386. Then let us see the floating point data registers in details, so that the understanding of the instruction will be easy. The 8087, it has got 80-bit individually addressable data registers, so organized as stack registers. So here they are called as the stack registers because the organization is just like the stack. Then mathematical operations are performed in these registers and can access these registers independently. All the instructions can access the. Then data registers are divided into 3 fields, that is sign, exponent and significant. Sign field is 1 bit, exponent field is 15 bits, and significant is 64 bits. So when 8087 receives a numeric data words, it stores and holds them in a format called temporary real form, and this is expressed as a product of 64-bit significant base, then 15-bit exponent, and the MSB, that is the sign bit, to represent either a positive or a negative number. Then the instructions automatically convert data into this format when loading the register and return back to the other format when returning to the system memory. So this we'll see when we actually take the examples for the instructions. Then let us understand the difference between the floating point unit register set and 8086 or 80386 register set. Now the biggest difference between the floating point register set and 80x86 register set is stack organization. So stack organization means what? Let us understand it. So in 86 or 386, the AX register is always AX register. But in 80x87, the register set is an 8-element stack of 80-bit floating point values. So it will be 8-element stack, and all are 80-bit floating point values. And in that, ST0 refers to the atom on the top of the stack. Then ST1 refers to the next atom, and so on. Now using the index to the stack pointer will refer to the each register. So because of this index, that is the TOP 3 bits index will refer to the top of the stack. This is called as relative stack addressing. So let us understand this from the figure. So here you can see we are having the registers R1 to R8 are shown here, R1 to R8, and they are designated, say ST0, ST1, ST2, ST3, then ST4, ST5, ST6, ST7. Now here any register can be at the top of the stack at any time. So this you must first understand, because the top of the stack is indicated by ST0. So when the index is 0, that will represent the top of the stack, and this index is a 3-bit, as I already told you. So those 3 bits are top bits in the control register. So the push operation loads the data at the top of the stack from the memory, and the data loaded now sits at the top with each of the other register pushed down by one position. So now here we are shown the top before the load instruction. So it is pointing to, it will point to ST0 always, top of the stack, but it is actually the R5 register. Now when we say push data onto the stack, now here the top of after it has changed to R4, but still this will be represented as ST0. Now how it will be doing it? The data and the reverse operation pop from the stack causes contents of ST0 to be transferred to memory, and all registers are moved up by one position. So when we do the pop operation, all registers are moved up, and when we do the push operation, at that time all the registers are pushed down. So when it is moved up, that is ST1 will become ST0, ST2 will become ST1, and so on. So here you can see whatever is the initial, after the load instruction, this will change. Now here it was ST0, R5 was ST0. Now R5 has become ST1, like that. So the operation is a relative, this is called as the relative stack addressing. That's why we can use all the 8 registers for the top of the stack, and it will depend on this index. So ST0 will always represent the top of the stack, and we can what we can change the registers for the top of the stack. So the top of the stack, any register can be at the top of the stack at any time. This is very important. Then let us go to the floating point data types. Here we have 3 floating point data types. The single precision floating point, which is having the fraction part and the exponential part and the sign part. Now this will be single point, so total is 32 bit. Then double precision floating point, it will have again the same 3 parts, but here the total bits will be 64. Then the double extended precision floating point, it will again have the same 3 parts, fraction, exponent and sign, but it will be 80 bits. So these are the 3 floating point data types. Then integer data types. Now in integer data type, we have the word integer or 16 bit, that will be having the sign 1 bit and other bits are 15 bits. Then double word integer, you will again have the sign bit and rest of them are the other bits. So this will be 32 bit, that is called a double word. And then we have the quad word, that is 64 bit. So these are the 3 types of integer data types, and one more, that is packed BCD integer. So that is 80 bits, and it will have the D0 to D17, that is 18 4 bits BCD digits. So that will occupy 76 bits, 72 bits, and then rest of that will be the sign. So in this way, these are the integer data types. Then let us go to the rounding part. Okay, the coprocessor attempts to round an infinitely accurate result from the floating point calculations. So rounding nearest to even, that is round towards the closest one. If both are equally close, round to the even one. Then round down, that is round towards minus infinity. Round up means round towards plus infinity, and rounds towards 0, that is truncation. So if you take example, we have a fraction and the calculated value is plus 1.011. Rounding up by adding 0.001 produces 1.100. And then rounding down, that is subtracting 0.0001 produces 1.011. Now this rounding will depend on the bits. So this we had discussed the rounding part, control bit, control register. So here you can see the original value and the rounded value. So rounding to nearest even, it will give us 1.100. Then rounding down will give us the 1.011. Then rounding up will give us 1.100. Round and truncating will give us 1.011. So rounding down and truncation, these values are same here. Similarly for the negative, here rounding nearest even 1 minus 1.100, and rounding down will also give us the same value, whereas the rounding up and truncate will give us this value. So this is how the rounding will be performed. Then classification of instruction set. The 8087 instructions are divided into 6 different groups: data transfer group, arithmetic instructions, comparison instructions, transcendental instructions, constant instructions and coprocessor control instructions. We will see today the data transfer instructions only. Then the other instructions, arithmetic, comparison, then transcendental, constant, they will be taken in the next videos, because it's not possible to cover all the instructions in a single video. Then the data transfer instruction, let us see. They are further divided into floating point data transfer, integer data transfer, and BCD data transfer. Let us see first the floating point data transfer. So the FLD, that is load real. So loads the 32-bit, 64-bit, and 80-bit floating point. So these are the three data formats for floating point, and that will be loaded to the top of the stack, that is ST. Then stack pointer is then decremented by 1. So when we load the data, the stack pointer will be decremented by 1. If you take the example, here you can see FLD ST7. Now this is the example. So here the register 7 is loaded onto the top of the stack, or it is copied to the top of the stack. Then similarly we have FLD memory 32. So here the contents of memory, that is 32-bit memory, is copied to the top of the stack, or ST0 particularly. Then next instruction is the FST, that is store real. This instruction stores current content of the top of this register to the specified operand. So here during copy, the data rounding occurs using rounding control bits in the control register. So just now we have seen the rounding. So when the copy operation is going on, at that time this data rounding will be done as per the control bits in the control register. So here if you take the example FST ST4, so here we are specifying ST4, that is the instruction data register ST4. So the top of the stack, that is ST0, it will be copied to ST4. So the 8 registers, data registers, can be used in this way. Then similarly the FST memory 64, here the top of the stack is copied to memory, which is 64-bit. So when copying, the rounding will be done. Then next instruction is FSTP, that is store floating point number and pop. So this instruction stores the copy of top of the stack into the memory or specified coprocessor register and pop the data from top of the stack. So here the data will be taken from the top of the stack and transferred to the specified register. So if you take the example FSTP, now here we are taking ST6, that is the register 6. So the top of the stack is copied to ST6. Then similarly FST memory 32, the top of the stack is copied to memory 32. Then next example is, say, next instruction is FXCH, that is exchange instruction. The FXCH instruction exchanges the contents of specified register with the top of the stack. Now again here you can see the most of the instructions are with the top of the stack. So that is ST index is 0. So here if you take FXCH, that is ST2. So the top of the stack and ST2, they are exchanged. So the registers, data registers, they can be used independently. So here the top of the stack is exchanged with the ST2. The contents will be moving from ST2 to top of the stack and top of the stack to ST2. Then let us go to the integer data transfer instruction. Now during transferring the data, the coprocessor atomically converts extended floating point numbers to integer data. So here, while the data registers are floating point, and we can use the integer data types also. So there are three types of integer data transfer instruction. There is FLD, FILD, FIST and FISTP. Now here you have to note, when there is no say any other alphabet. Now here we have added in alphabet I, that is for the integer. FLD was for the floating point. So FILD is for the integer type. It will be common for most of the instructions. Then let us see the FILD instruction. It is load integer, loads a 16-bit, 32-bit or 64-bit. These are the three types of integer data. So they are loaded to the top of the stack, and stack pointer is then decremented by 1. So if you take the example FILD ST3, it will load register 3 or ST3 to the top of the stack and then decrement the stack pointer by 1. So once the stack pointer is decrement, the top of the stack will change. It will be the next top of the stack will be the next register. Then next instruction is FILD memory. So here the memory is, the contents of memory is copied to the top of the stack, and here it is similar to FLD, but the data here is integer. Then let us go to the integer data transfer instruction, that is FIST and FISTP, store integer and pop. Now these instructions work in exactly similar manner with FST and FSTP, except that the operands are integer operands. So if I take the example FIST ST5, now here we are referring to register 5. So the top of the stack is copied to the ST5. Then FIST memory 64, top of the stack is copied to memory 64. Then BCD data transfer. The 8087 or 387 has two BCD data transfer instruction, FPLD and FPSTP. Only two are there here, FPLD and FPSTP. So these load and store 80-bit BCD values. They are for the particularly the BCD data type, 80-bit. Then FPLD converts BCD to its 80-bit extended precision equivalent and pushes the result onto the stack. And FBSTP, it will pop the extended precision real value on the top of the stack and convert it to BCD value. So again rounding according to the bits of the floating point control register, and stores the converted result at the address specified by the destination operand. So here again the conversion rounding will be there, and it will convert to the particular BCD value, and then it will store. So, and here you should note that there is no only FPLD and FBSTP, only two instructions are there. Other instructions are not here for the BCD. So when we take the example here, if you want to convert 80-bit BCD value to a 64-bit integer, then we can use the FBLD instruction. So FBLD BCD 80. So here we are getting the BCD value to convert, and when we give this instruction, it will be going to the top of the stack. Then when we give this FIST memory 64. So that is for storing integer. So it will be stored as an integer, which will be 64 bit. So the top of the stack will be stored as an integer into the memory. So in this way we can convert 80-bit BCD value into 64-bit integer. So this is how the instructions will work. So with this we come to the end of this video. If you have any questions, you can contact me on Facebook, Twitter, Gmail or Instagram. Then if you like the video, press the like button, share with your friends and subscribe to our channel Engineering and Technology for You, and press the bell icon if you want to get notifications for future videos. And thanks for watching.